Hi there, year 10. Again, not able to be there. So if we can get this down as normal, it is D-Clean, it's the 23rd of Tachwedd. We're going to be doing some work on the national grid today, and our keywords are supply, transmission and transformers. You do know activity. Obviously pause within this video now. So you do know activity is name all 8 types of energy. Okay, we remembered a mnemonic to remember these 8 types. So we use the first letter of each one of those. It's in your books. Describe the energy transfer in a car. Be careful on this one. Okay, as you'll see. And then the third one, I've got 12 volts there. I've got 3 ammeters, ammeter 1, ammeter 2, ammeter 3. And I've got 2 bulbs, bulb 1, bulb 2. So question A is, if A1, if this one is 6 amps, what's this and this going to be? The current, what's the current? And then question B then, if the voltage over bulb 1, if I put a voltmeter over here, and it's 5 volts, what is this one going to be? Then question 4, oops, I didn't want to do that. Question 4 then is, if there's 900 going in, 700 is wasted, okay? What's this useful energy going to be? Once you found that, you can calculate the efficiency. So calculate efficiency there. You're probably going to need a calculator for that, looking at the numbers there. And then your challenge question, calculate the total resistance. And yeah, you're definitely going to need a calculator for this one. So you may as well give out the calculators while we're at it. Okay, so I'm just going to put that on the screen now again. So again, you can pause when you want. And then we're going to be going to the answers. Lovely. Okay, let me just scroll up here. So look for the answers now. So name all types of energy. Kinetic, electric, kinetic, heat, light, gravitational, chemical, sound, and elastic. Remember, English kids hate learning GCSE. And that's how we're going to remember them. Like I said, you're not going to get any marks for remembering these, but they do help when it comes to energy transfer now. So describe the energy transfer in a car. Okay, it's going to be one of these 8 that you're going to be using here. Well, petrol is chemical energy. It's stored chemical energy. You've got to fill your car up, okay? Unless you've got a hybrid, then you could have electrical there. So a hybrid, like an electrical car, an energy efficient car. But usually we're set 90% or 99% of the vehicles on the road at the moment are still using petrol. Now that's going to get converted into movement, which is obviously the useful energy here. Sound, you can hear a car or you can hear a van, but that's wasted energy. And heat from the engine is a wasted energy. Now, I should have really said in an engine rather than a car, because I'm sure some of you have got now plus electric for the lights and plus sound for the maybe the radio, and more kinetic for the windscreen wipers and things like that. But we're just focusing on the movement there. Question 3 then. If it's 6 amps at this ammeter, this is going to be 6, and this is also going to be 6, because it's the same. In a series circuit, SCS, series, current, the same, okay? Because it's just one after the other. And then if the series, if the current is the same, the voltage adds up. So the supply voltage is 12 volts. I've got 5 here. 5 plus something is going to give me 12, and that is going to be 7 volts. Here's your Sankey diagram. I've got 900 joules going in. I've got 700 being wasted. So 900 minus 700 is going to give me 200 useful. So this is not very efficient because it's wasting way more energy than it's producing to be useful. So calculate the useful energy, calculate the efficiency there is useful over total. So that's going to be 200, which is our useful there, over the 900 going in, times 100, it comes out to 22%. Your challenge question then is the resistance in a parallel circuit. You've got to use 1 over RT here. So you would plug that into the calculator. Again, there's 2 ways you can do that. You can either 1 over 6 plus 1 over 6 in the calculator using the fraction button, or you can just put 1 divided by 6 equals and then write the answer, plus 1 divided by 6 equals and then and then you get 1 over RT equals 0.334. Now, that is 1 over RT. It's not RT yet, so you've got to divide this answer by 1 now to get R on its own. RT, T meaning total. So 1 over 0.334 is 3 ohms. So it comes out to be like 2.9997. But I've rounded up to 3. And that makes sense because it's going to be half. In a parallel circuit, the total resistance decreases the more resistors you add. So if I added another resistor on the bottom here, this number would go down again. It would get less. Okay, let's move on to the lesson then. So we're going to do the main features of the national grid. So I'd like you to, if I was there now in the classroom, okay, I'd be doing this. I would have written this. The only difference is that I've set it all up beforehand. So I would like you to get this in your books as neatly and tidily as you can, because it's very important to have in your books, because it does show each step. And it's common to have a diagram like this. So with your pencils and your rulers, I mean, it's not difficult to draw these. The main things we want to get is the step-up transformer there, the step-down transformer there. Okay, they're just little squares. We can draw them as. You've got your pylons here carrying the cables for the national grid. And obviously, this is a very simplified version. You've got your home and you've got the power station. So the power station is where it all happens. I'm going to show you how it happens a bit later in the lesson now. Your power station is running at 25,000 volts. That's a number we need to remember. Okay, probably come up as a multi-choice question. The step-up transformer is going to step that voltage up. It's going to increase the voltage there. And I'll tell you why. It is to reduce the current. If we reduce the current, we're going to reduce energy lost as heat. So I would get that down in your book somewhere as well. Okay, very important. Common question, why do they use a step-up transformer to pump it up to this ridiculous amount of volts? That's why they try and have it overhead, because you shouldn't be touching. You shouldn't be near these step-up and step-down transformers. You often see them behind metal fences with danger, do not enter, okay? So it's usually the step-down transformer you're going to see by your homes. So power station goes to your step-up transformer. This steps up the voltage, okay? Carries high voltage across the country. And the national grid is all connected as well. And we're going to talk about that at some other time, okay? They're going to come up in questions. And then you've got this step-down transformer there. Now, there's a number of things it can step it down to, because using factories, they use three-phase power. But we're going to just concentrate on the 230 volts, which is a number you have to remember as well, which we use in standard homes and in your classroom now. So if you was to charge your phone on the side, it's going to be using 230 volts. Okay, so that's down in your book. I'm going to push on now to the next bit, which is calculating power. So this is the other bit that we have to do now. So here's an example. Again, I'd really like this example in your book because it's a typical example and it doesn't take long. So I've written there the example. A power station, like we just saw, produces 300 million watts. Now, there's other ways we can write this, but I'm just going to stick to a simplified version at the moment, because you might see that as 3 times 10 to the power 1, 2, 3, 4, 5, 6, 7, 8, okay? 3 times 10. In fact, I might write that there now. 3 times 10 to the power 8. You might see that number. Of power with a current of 4,000 amps. Again, you might see this number, and I'll do this in red this time, as 4 times 10 to the power 3. Okay, because there's 3 zeros after 4. Calculate the voltage produced. There's also a way we can write that into the calculators, and I've got a video on this as well. But we're just going to stick with these big numbers first. So what I would do, I would get this from the front of my exam book on page 2. I would put it in a triangle. Again, I've got a video to show us how to do that. But if P is on the top of I already, then P stays on top. And it's asking us to calculate the voltage. Well, it's already in this format anyway, so V equals P over I. So your power, which is this, goes on top. And then your I, which is your current, is 4,000, goes on the bottom. that's going to equal, in your calculators, 75,000 volts. Now it's worth remembering this for a second. This is not a number you have to remember, but we're going to, when you try something now, you can see what happens there, okay? So I think that's a fairly easy equation and calculation to do. So I'm not going to give you a pile of these to practice because it would be pointless. But I have got this question set up now that I'd like you to try. So it's a little bit of a challenge if you see it as this. It says the transformer increases the voltage. So this, now what it produces, increases by a factor of 6. So this increases 6 times. What is the output current now? So it wants to know what is the current. So you'd put your finger over I. Now it's going to be P over V. Remember, the power stays the same. I'd like you to have a go at that. It says they assume that the transformer is 100% efficient because, as we know from Sankey diagrams, not all energy transfer is efficient, okay? Some energy is lost. But we're going to pretend that it's 100% efficient and that no energy is lost here. So these numbers now are fixed. So this increases 6 times. This stays the same. What is the current? Have a go. All right then, so hopefully you've got something written like this. So I've identified my voltage. Oops, didn't want to do that. I've identified my voltage as 75,000, but it increases by a factor of 6. So I've taken that now to 450,000 volts. Then my power was fixed, as we said. It was 300 million. I should have put watts there maybe. Watts. And then my current, I don't know what it is. So I put my finger over I, it's P over V. I equals P over V equals 300 million over 450,000. That's going to give me 667 amps. Is this less than my other one? Well, my other one was 4,000 amps, wasn't it? Remember, current was on the bottom. So if I've increased the voltage here, my current has gone down. It's reduced. So 667 is much smaller than 4,000. So just as a quick sort of recap there, if you increase the voltage here, then the current is going to get smaller. Less heat lost, less heat wasted. Okay, on to the final page then. So let me just scroll up here. Now again, we've got another little diagram. I've added some colour here. Okay. Oops, just dropped my iPad a little. So how electricity is generated is your subheading there. So I've got a little diagram and it starts with your fuel really. Your fuel is put in. So any power station now runs like this, whether it's nuclear power. So this is your fuel. This could be nuclear, or it could be coal, it could be gas, it could be anything, okay, go in there. So that's going to be heated out. Well, it's going to burn because it's a fuel, okay, so it's going to burn, and then it's going to warm water, and this is a really simplified diagram. So it's going to boil some water. The steam from the water then is going to turn this turbine. So that's going to start to turn in. This is connected now. There's a little magnet in there with a coil of wire around it. And I don't know if you know this, but if you turn a magnet in a coil of wire, it produces a current, it produces electricity. So you can call it a generator. So this is attached to a generator, which is then, okay, going to go to your step up. So this is your power station, all this by here. And then your step up transformer is going to step that voltage up and then off to the national grid and so on. So what we need to know is the steps now. And again, this is a common 4 marker, sometimes put in a 6 marker. But I've only ever seen it in a 4 marker up to now. It would say, describe how a power station generates electricity. So fuel is burnt to boil the water. Okay, that's that step. Step 2, steam makes the turbine spin. So the steam here makes the turbine spin. The movement of the turbine turns the generator in there, the magnet and the coil of wires, and then the generator produces electricity. And that is it, really. Okay, I think there's an OMG video on this as well, linked with the national grid. And then we've got the energy transfers within the power station then. So coal is a chemical energy, it's chemical stored potential there. Then as it boils the water, you've got thermal, okay? That thermal heat. That's going to turn into the steam kinetic, which drives the turbine kinetic movement, which generates electricity. And that's your 4-step energy transfer as well. Get that in your books, very important. Now we're going to do some practice on this on the AQ, on the All Questions booklet, which we're going to do next. Now you've done the foundation ones with me when you were off for a week just after half term. So we're going to go to the higher paper now, and you're going to watch a video of me doing that. But before we do that, just get the what went well, even better if in today. So your work is nice, complete, your books are all nice. So there it is. What went well, I'm able to describe how electricity is made in a power station. Even better if, discuss the advantages and disadvantages of non-renewable energy. And I guess that is our next lesson, okay? So well done, and I will see you very soon.